The cosmos is flying apart faster every second. This accelerating expansion is one of the greatest mysteries in science, governed by a single, elusive number called the Hubble Constant. You are about to uncover 30 astonishing facts that will completely reshape how you see reality, from the universe's fiery birth to the dark energy tearing it apart. You will learn why the universe's expansion rate is sparking a crisis in cosmology and what it reveals about our ultimate fate. Why does our own measurement of the cosmos contradict the story told by its ancient light? How much of the universe is made of stuff we cannot even see? What does it feel like to live in a universe that is actively and increasingly trying to empty itself? Edwin Hubble made a discovery in the 1920s that shattered our static view of the cosmos. He found that galaxies are not simply drifting in space, they are fleeing from us, and the farther away a galaxy is, the faster it appears to be receding. The evidence for this incredible motion is written in the light of these galaxies. Their light stretches as it travels across the vastness of space, shifting toward the red end of the spectrum, much like the sound of a siren deepens as an ambulance speeds away from you. This cosmic redshift is not because galaxies are moving through a fixed space, like cars on a highway. Instead, the fabric of space itself is stretching, carrying the galaxies along with it. Think of the universe as the surface of a balloon being inflated. If you draw dots on that balloon, each dot represents a galaxy. As you blow air into the balloon, every dot moves away from every other dot. No single dot is at the center of the expansion. The entire surface is growing. This is precisely what is happening to our universe on a colossal scale. Space is expanding everywhere at once, pushing the cosmic structures within it ever farther apart. This leads to a profound and often misunderstood truth about the Big Bang. It was not a conventional explosion that hurled matter out into a pre-existing void. There was no central bomb, no point of origin we can point to in the sky. The Big Bang was, and still is, an explosion of space itself. From our vantage point on Earth, we see every distant galaxy rushing away from us, which might feel like we are at the center of the universe. But here is the crucial part. An observer in any other galaxy, in any corner of the cosmos, would see the exact same thing. Everyone sees themselves as the center of the cosmic retreat. To truly grasp this, picture the universe not as a star field, but as a vast, flexible grid. Each intersection of the grid holds a galaxy. Now, imagine the entire grid stretching uniformly in all directions. The space between every single intersection grows. From the perspective of any one galaxy, all the others are moving away, and the farther away they are on the grid, the more space there is to stretch, so the faster they appear to recede. This means we are not in a special, central location. We are simply riding the fabric of an expanding grid, witnessing the same universal stretch that every other galaxy is experiencing. The cosmos has no center, and its expansion is a fundamental property of space everywhere. This universal stretching is measured by a single, crucial number known as the Hubble Constant. Think of it as the speedometer for the entire cosmos, giving us the current rate of the universe's expansion. Its value is expressed in a unit that sounds complex but reveals a beautiful simplicity: kilometers per second per megaparsec. A megaparsec is an almost unimaginable distance, roughly 3.26 million light years. So, what this unit means is that for every additional megaparsec of distance between us and a distant galaxy, that galaxy appears to be receding faster by a certain number of kilometers every second. If the Hubble constant was 70, for instance, A galaxy 1 megaparsec away would rush away at 70 kilometers per second. A galaxy 2 megaparsecs away would be moving at 140 kilometers per second, and so on. This single number is one of the most sought-after prizes in all of science. It is not just a measure of speed, it is a key to unlocking the universe's deepest secrets. By knowing how fast the cosmos is expanding today, we can essentially run the film of the universe backwards to calculate the moment it all began, revealing the age of the universe itself. Furthermore, this constant helps us forecast the ultimate fate of everything. Will the expansion continue forever, slowing to a crawl, or will it accelerate until the very fabric of reality is torn apart? The Hubble Constant holds the answer, making its precise measurement one of the grandest and most urgent quests in modern cosmology. Yet for all its groundbreaking power, Edwin Hubble's original measurement was profoundly wrong. His first calculation of the Hubble constant gave a value of around 500 kilometers per second per megaparsec, a number so large it sent the scientific world into a quiet uproar. If that number had been correct, it would have meant the universe was only about 2 billion years old. This created an impossible paradox, because geologists already knew, from studying radioactive elements in rocks, that the Earth itself was far older than that. The cosmos simply could not be younger than the planet it contained. The error did not lie in Hubble's brilliant idea, but in the fiendishly difficult task of measuring cosmic distances. His work relied on a specific class of stars called Cepheid variables, which pulse in a regular rhythm. The key was that the true brightness of a Cepheid is linked to its pulsation period, a relationship discovered by Henrietta Leavitt. By comparing how bright a distant Cepheid appeared in his telescope to its known true brightness, Hubble could calculate its distance, but his measurements were flawed. He mistook dimmer, distant Cepheids for brighter, closer ones. He was also unaware of a whole class of interstellar dust that dims starlight, making stars appear farther away than they truly were. These errors compressed his cosmic map, making the galaxies seem closer together. When he then measured their redshift velocities, the expansion rate appeared terrifyingly fast, like a movie played on fast forward. This initial blunder set the stage for a 70-year-long detective story, a meticulous refinement of our cosmic ruler that continues to this very day. So how do we measure these mind-bending distances with any accuracy? The answer is a tool of breathtaking ingenuity, the cosmic distance ladder. This is not a single instrument, but a chain of interconnected methods, each one carefully calibrated by the one before it. We build our way out into the cosmos, one careful step at a time. The first rung of this ladder is a technique you can demonstrate with your own thumb. Hold it at arm's length and close one eye, then switch eyes. You will see your thumb appear to jump back and forth against the background. This is parallax, and it works for stars too. By observing a nearby star from opposite sides of Earth's orbit around the Sun, astronomers can measure its tiny apparent shift against the more distant stellar backdrop. This gives us a direct, geometric measurement of distance for stars within a few thousand light years. It is a solid foundation, the first and most certain step on our ladder. Once we know the true distance to these nearby stars, we can identify a special class among them, the Cepheid variables. These are stars that pulse in brightness with a clockwork regularity, and their true brilliance is tied directly to the rhythm of their pulse. A Cepheid that pulses slowly is intrinsically very bright, while one that pulses quickly is dimmer. This period luminosity relationship, discovered by Henrietta Leavitt, is the master key to the second rung of the ladder. By studying Cepheids whose distances we already know from parallax, we calibrate their true brightness. Then, when we find a Cepheid in a far-off galaxy, we simply measure its pulse rate to know its true power, and compare that to how dim it appears to us. The difference tells us the distance to its host galaxy. This carries us across millions of light years. But to reach the truly ancient galaxies whose light holds the expansion history of the universe, we need an even brighter beacon. This is where the final, most powerful rung of the ladder comes into play, the Type Ia supernova. These are stellar explosions of such consistent, cataclysmic power that they can outshine an entire galaxy. They occur in a binary star system where a dense white dwarf star steals material from its companion. Once it reaches a very specific, critical mass, it undergoes a thermonuclear detonation. Because this critical mass is always the same, the brightness of the resulting explosion is always nearly identical. A Type Ia supernova is a perfect standard candle. By finding these supernovae in galaxies whose distances we already know from their Cepheid variables, we can confirm their true, staggering luminosity. Then, we can spot them in galaxies so distant their light has been traveling for billions of years. Even from that incredible range, we can measure their faint glow and know precisely how far away they are. This ladder, from parallax to Cepheids to supernova, is the only way to build a reliable map of the expanding universe. But its strength is also its greatest vulnerability. A tiny, almost imperceptible error in the first rung, in the parallax measurement of a single star, propagates upward. It throws off the calibration of the Cepheids, which in turn misjudges the power of the supernova. Like a carpenter's level that is off by a single degree, the entire cosmic construction can be thrown out of alignment, leading to profound uncertainty in the Hubble constant itself. Henrietta Leavitt discovered the key to the cosmos in the rhythmic heartbeat of distant suns. While working at the Harvard College Observatory in the early 1900s, she studied photographic plates of stars in the Small Magellanic Cloud, a small satellite galaxy of our own Milky Way. She focused on a special type of star called a Cepheid variable, which grows brighter and dimmer in a perfectly regular cycle. Leavitt made a stunning connection. She found that the pace of this stellar pulse was directly tied to the star's true intrinsic power. A Cepheid that pulses slowly over a period of many days or weeks is inherently a brilliant giant. A Cepheid that flickers rapidly with a short pulse period is a far dimmer star. This period luminosity relationship was a monumental breakthrough. It meant that by simply clocking the rhythm of a Cepheid's pulse, an astronomer could know its true brightness with certainty. This transformed these stars into the first reliable standard candles for measuring the universe. A standard candle is an object whose true brightness is known. Imagine you are looking at two identical light bulbs. One is close to you and the other is far away. The farther bulb will appear much dimmer. If you know that both bulbs are 100 watts, you can use how dim the distant one appears to calculate exactly how far away it is. This is precisely what astronomers do with Cepheid variables. They measure the star's pulse period to learn its true wattage, then compare that to its apparent, faint glow in the telescope. The difference reveals the staggering distance to the star's host galaxy. This method, born from Leavitt's meticulous work, became the crucial second rung on the cosmic distance ladder. Edwin Hubble used it to find Cepheids in the Andromeda Nebula, proving it was a separate galaxy far beyond our own, and forever changing our understanding of the universe's scale. Yet for decades, Observing these vital stars in more distant galaxies was nearly impossible from Earth's blurry atmosphere. The Hubble Space Telescope, orbiting high above that atmospheric distortion, changed everything. Its crystal-clear vision allowed it to pick out individual Cepheid variables in galaxies tens of millions of light-years away. By carefully measuring their pulses and their apparent brightness, the Hubble telescope provided a massive leap in precision, tightening our grip on the cosmic distance scale and bringing the true value of the Hubble constant into sharper focus than ever before. The most perfect cosmic explosions are the type Ia supernova. These are not the chaotic deaths of massive stars, but the meticulous, predictable detonations of stellar cinders called white dwarfs. A white dwarf is the dense, Earth-sized core left behind when a sun-like star dies. In a binary system, this white dwarf can act as a gravitational thief, slowly siphoning material from its companion star. It grows heavier and heavier until it reaches a very precise, critical mass limit. At that exact moment, the entire star is consumed by a runaway thermonuclear inferno. This explosion is so uniform and so cataclysmic that it always releases nearly the same amount of light. It is as if nature has provided us with a series of 1 billion watt light bulbs scattered across the cosmos. This consistency makes type Ia supernova the ultimate mile markers for the deep universe, far brighter and more powerful than even the Cepheid variables. Astronomers can spot their brilliant flash in galaxies so remote their light has been traveling for billions of years. Because we know their true, staggering brightness, we can measure how dim they appear from Earth and calculate their distance with remarkable precision. They form the final, most powerful rung on our cosmic distance ladder, allowing us to map the expansion of the universe across vast stretches of both space and time. But in the late 1990s, two independent teams of astronomers used these perfect explosions to make a discovery so shocking it won them the Nobel Prize. They were not trying to measure the expansion rate itself, but to see how much the universe's gravity had slowed it down over time. They compared the apparent distance of extremely far away supernova, whose light was emitted billions of years ago, to the distance expected from their redshift. The result was breathtaking. The distant supernovae were fainter than they should have been, meaning they were farther away than anyone had predicted. The expansion of the universe was not slowing down at all. It was speeding up. This was like tossing a ball into the air, expecting it to fall back, and instead watching it shoot faster and faster toward the sky. The universe was being pushed apart by a mysterious, repulsive force, a discovery that would turn all of cosmology upside down and introduce us to the greatest enigma in modern physics, dark energy. That name, the Hubble Constant, is actually a bit of a cosmic misdirection. It is not truly constant across all of time. The expansion rate of the universe has a history, a dramatic story of push and pull that is still unfolding. In the beginning, the cosmos was dense and filled with matter and radiation. Their collective gravity acted like a universal brake, relentlessly pulling on the fabric of space and slowing down the initial, ferocious expansion from the Big Bang. For billions of years, gravity was winning the tug of war. But then something shifted. Around 5 billion years ago, the universe had stretched and thinned out so much that the weakening grip of gravity could no longer hold sway. A mysterious, repulsive force began to dominate. This is dark energy, and it behaves like an anti-gravity agent woven into the vacuum of space itself. As the universe grows larger, there is more vacuum, and thus more of this repulsive force. So while gravity's influence fades with distance, dark energy's influence grows stronger. This is why the expansion is now accelerating. The value we measure today, the Hubble constant, is merely a snapshot. It is the current reading on the cosmic speedometer, the expansion rate at this specific moment in the universe's 13.8 billion year life. It is the result of this epic battle, a battle that dark energy is now decisively winning, forcing the cosmos to fly apart faster with each passing second. While we build our cosmic distance ladder step by step from the nearby universe, another mission took a completely different approach, looking back to the very beginning. The European Space Agency's Planck satellite was a time machine designed to capture the oldest light in existence, the cosmic microwave background. This faint glow is the cooled remnant of the Big Bang's fireball, a fossil imprint from when the universe was just 380,000 years old. Planck mapped this afterglow with exquisite sensitivity, measuring its minute temperature fluctuations, the hot and cold spots that speckle the cosmic canvas. These tiny ripples are a frozen record of the infant universe's density, a blueprint from which everything we see today would eventually form. By analyzing this blueprint through the lens of our best cosmological model, scientists could run the entire cosmic simulation forward. They could calculate how gravity would amplify those tiny seeds into galaxies and clusters, and crucially, how the tug-of-war between dark matter and dark energy would shape the expansion rate over 13.8 billion years. This process gave them a prediction for what the Hubble constant should be today, a value derived not from looking at nearby galaxies, but from the primordial conditions of the cosmos itself. Planck's prediction was a triumph of precision, a number so exact it seemed to lock in our understanding of the universe. Yet this very precision would ignite a firestorm in cosmology, because when astronomers measured the expansion rate using their cosmic distance ladder, they got a different answer. The universe today was not behaving as the ancient light said it should. This single number, the Hubble constant, has become the focus of a profound cosmic disagreement. We now face a puzzle so deep it is known as the Hubble tension. On one side, we have the meticulous work of the cosmic distance ladder, measuring the expansion rate using Cepheid variables and type Ia supernova in our local modern universe. This method gives us one specific number for how fast space is stretching right now. On the other side, we have the pristine data from the Planck satellite, which studied the ancient cosmic microwave background. By understanding the physics of the infant universe and running the cosmic simulation forward, Planck predicts what the expansion rate should be today. These two methods, one looking at the nearby cosmos and the other gazing back to the dawn of time, should arrive at the exact same answer, but they do not. The local measurement from supernova and Cepheids suggests the universe is expanding faster, by about 10%, than the early universe data implies. At first, scientists hoped this was simply a measurement error, a tiny flaw in one of the rungs of the distance ladder, or a subtle miscalibration in the satellite's instruments. But after years of rechecking, refining techniques, and eliminating known sources of error, the discrepancy has not gone away. It has stubbornly persisted, growing into a full-blown crisis in cosmology. This is not a minor accounting error. It is a fundamental clash of observations. It is as if you dug up a 1,000-year-old tree stump, counted its rings to predict how tall the tree should be today, and then went outside to find the living tree is actually 10% taller than your prediction. The laws of physics you used to make that prediction are suddenly in question. This tension suggests that our standard model of cosmology, which has been so successful for decades, might be incomplete. There could be something we do not understand about dark energy, perhaps that its strength has changed over time, or there might be a new, previously unknown type of particle or field that began influencing the cosmos long after the Big Bang. The Hubble tension is a glaring clue, a crack in the foundation of our understanding, pointing toward new physics waiting to be discovered. One camp in this cosmic standoff is the SH0ES team, a group of astronomers dedicated to measuring the Hubble constant with relentless precision. Their approach is built on the cosmic distance ladder, a direct measurement of the universe as it is today. They train the sharp eyes of the Hubble Space Telescope, and now the James Webb Space Telescope, on nearby galaxies. They hunt for Cepheid variables, those reliable pulsating stars, and use them to calibrate the even brighter Type Ia supernova in those same galaxies. This creates a rock-solid chain of measurement that stretches right out into our modern cosmic neighborhood. Their result is a number that feels immediate, a reading taken from the current state of the cosmos. It is like checking the speedometer on a car to see exactly how fast it is moving at this very moment. The other camp relies on a completely different kind of evidence, a fossilized echo from the dawn of time. This method uses the cosmic microwave background, that ancient light from when the universe was just 380,000 years old. The patterns in this afterglow are a detailed blueprint, and our standard model of cosmology is the instruction manual. By feeding this blueprint into the model, scientists can run the entire history of the universe forward in a supercomputer simulation. This predicts how fast the cosmos should be expanding today, based solely on its initial conditions. This is not a direct measurement, but a profound inference, like predicting an adult's height from a detailed scan taken at birth. Both methods are the pinnacle of scientific achievement, refined over decades to an astonishing degree of accuracy. Yet they stubbornly disagree. The local measurement suggests a faster, more frantic expansion, while the early universe prediction points to a slightly more sedate pace. This is not a matter of one being right and the other wrong. It is a clear signal that our instruction manual, the standard cosmological model, might be missing a page. Perhaps dark energy is not constant, but has grown stronger over time. Or maybe an unknown type of neutrino or another exotic particle was stirring the cosmic pot in the universe's adolescent years. This tension is the most exciting thing in modern cosmology because it is not an error. It is a clue, a direct invitation to uncover a deeper layer of reality. Perhaps the simplest explanation is that we are just making a mistake. Could the Hubble tension be nothing more than a sophisticated accounting error, a subtle flaw in our cosmic bookkeeping that has fooled us into thinking we have discovered new physics? This possibility, while less thrilling than a fundamental revolution, is taken incredibly seriously by scientists. They spend years hunting for what are known as systematic errors, tiny biases or miscalibrations that could creep into our measurements. For the cosmic distance ladder, the chain is only as strong as its most uncertain rung. A nearly invisible haze of cosmic dust, for instance, could be dimming the light of Cepheid variables in distant galaxies. If we do not perfectly account for this dimming, we would think those stars are farther away than they truly are. This would throw off the calibration of the Type Ia supernova in those same galaxies, making the entire distance ladder too long. The result would be an overestimation of the expansion rate, creating a false tension with the early universe prediction. Similarly, what if our perfect standard candles are not so perfect after all? Type Ia supernova are remarkably uniform, but are they absolutely identical? Could there be slight variations in their explosions based on the age or composition of the white dwarf star that detonates? If the most distant supernova, which exploded when the universe was younger and composed of different materials, were intrinsically a little fainter than their modern counterparts, we would again misinterpret their distance. They would appear fainter, so we would place them farther away, leading us to believe the expansion was faster than it actually is. Teams like SH0ES are obsessively cross-checking their work, using the James Webb Space Telescope's infrared vision to peer through dust clouds and get a clearer view of Cepheid variables. They are comparing different types of stars and supernova to see if their results hold. So far, the tension persists, stubbornly resisting every attempt to explain it away as a simple error. This relentless scrutiny only makes the mystery deeper, forcing us to ask if the problem is not with our instruments, but with our very understanding of the cosmos. But what if the error is not in our measurements, but in our theory itself? The Hubble tension could be the first observable crack in our most fundamental model of the universe, lambda-cidium. This model, which has been the bedrock of cosmology for decades, describes a cosmos dominated by cold dark matter and a constant form of dark energy, the lambda. It has been spectacularly successful at explaining everything from the cosmic microwave background to the large-scale structure of the universe. Yet this very model is what we use to predict the Hubble constant from the early universe. If the prediction and the direct measurements stubbornly disagree, it suggests the model itself might be missing a crucial ingredient. This is where the mystery turns into a thrilling hunt for new physics. Perhaps dark energy is not the simple, constant force we have assumed. What if its repulsive strength has been increasing over billions of years? A form of dark energy that grows stronger would have given the universe an extra push, accelerating the expansion beyond what the standard model predicts for today. This would neatly explain why our local measurements show a faster rate than the ancient light implies. Another tantalizing idea involves dark radiation. This is not the light we see, but a hypothetical, invisible stream of fast-moving particles that flooded the early cosmos. Extra dark radiation would have altered how quickly the infant universe expanded, changing the initial conditions from which everything evolved. Running the cosmic simulation forward from this altered starting point would yield a different, and perhaps matching, prediction for the modern Hubble constant. Or maybe the two great unknowns are interacting. We have always treated dark matter, which clumps together through gravity, and dark energy, which pushes space apart, as separate entities. What if they are not? What if they can interact, exchanging energy in a way that subtly changed the expansion history of the universe? Each of these possibilities points to a cosmos far more dynamic and strange than our standard model allows. The Hubble tension is no longer just a number. It is a beacon, illuminating a hidden door in our understanding of reality. What lies behind it could redefine the fundamental forces that have shaped everything we see. Dark matter was the cosmic architect that built the universe we now observe, while dark energy currently dominates, driving the acceleration. For billions of years, it was the immense gravitational pull of dark matter that ruled the cosmos. After the Big Bang's initial fireball, the universe was expanding at a ferocious rate, but dark matter, an invisible substance that does not emit or absorb light, was everywhere. Its gravity acted as a cosmic brake, relentlessly tugging on the fabric of space and steadily slowing the expansion. This was the Great Deceleration era, a time when gravity was firmly in control. Without this invisible scaffolding, the universe would have expanded so rapidly that matter would never have clumped together. There would be no galaxies, no stars, and no planets. Dark matter provided the gravitational wells for ordinary atoms to fall into, creating the vast cosmic web of filaments and clusters that structure the universe. Every galaxy we see, including our own Milky Way, is embedded within a much larger, invisible halo of dark matter. Its presence is the only reason we have a cosmos rich enough to study, a universe with enough structure to even allow for the measurements that now reveal the Hubble tension. The very distance ladder we built relies on galaxies and supernovae that dark matter helped to form. So while dark energy now steals the spotlight with its strange, repulsive force, we owe the very existence of our cosmic map to the silent, persistent pull of dark matter. The universe was supposed to be slowing down. That was the fundamental expectation, the logical outcome of a cosmos filled with matter and ruled by gravity. Every galaxy pulls on every other galaxy, a cosmic tug-of-war that should have been gradually putting the brakes on the expansion that began with the Big Bang. The only question was whether this deceleration would be enough to eventually reverse the expansion in a big crunch, or if the universe would simply coast toward a gradual, cold halt. In 1998, two teams of astronomers set out to measure this cosmic deceleration by using the most reliable mile markers they had, Type Ia supernova. One team was led by Saul Perlmutter, and the other by Brian Schmidt and Adam Rees. They raced to find these perfect explosions in galaxies so far away that their light had been traveling to us for billions of years. By comparing how far these ancient supernovae actually were, based on their dimness, to how far away their redshift said they should be, they could measure the expansion rate of the young universe and compare it to today's rate. They expected to see that the distant supernovae were closer than anticipated, a sign that the universe was expanding more vigorously in the past before gravity slowed it down. But the data told a completely different and terrifyingly strange story. The distant supernovae were not closer, they were farther away. They were fainter than they had any right to be. This meant that billions of years ago, the universe was expanding more slowly than it is now. The expansion was not decelerating at all. It was accelerating. It was as if you dropped a pen, expecting it to fall to the floor, and instead watched it shoot upward toward the ceiling faster and faster. The result was so shocking that both teams spent months checking and rechecking their data, searching for any possible error, any overlooked source of dust that could be dimming the starlight, any flaw in their analysis. But the finding held firm. The cosmos was being pushed apart by a mysterious, repulsive force. This discovery earned Perlmutter, Schmidt, and Rees the Nobel Prize in Physics in 2011, and it forced us to confront a stunning new reality. The dominant component of our universe, making up about 70% of everything, is not matter, not even dark matter, but this inexplicable dark energy, an anti-gravity force that is actively and increasingly hollowing out the cosmos. This mysterious force, dark energy, is not a substance flowing through space, but a property of space itself. It is as if the vacuum of empty space possesses a fundamental, intrinsic energy that exerts a negative pressure, pushing the cosmos apart. The most straightforward explanation for this is a concept Einstein once called his greatest blunder, the cosmological constant. Represented by the Greek letter lambda, it describes a constant energy density that is woven into the very fabric of spacetime. This energy does not dilute as the universe expands. Instead, more space means more of this repulsive energy. This is why dark energy's effect is so counterintuitive. For most of cosmic history, the universe was a much smaller, denser place. The gravitational pull from all the matter and radiation packed into that smaller volume was immense, overwhelming the feeble push of dark energy. The expansion was steadily slowing down, but as the universe grew, stretching space to a vast, sparse emptiness, the matter and radiation thinned out, and their collective gravitational grip weakened. The repulsive force of dark energy, however, remained constant in every cubic centimeter of new space. Around 5 billion years ago, a cosmic tipping point was reached. The universe had expanded enough that the relentless, cumulative push from all that vacuum energy finally surpassed the fading pull of gravity. The brakes were off, and the accelerator was pressed. The expansion of the universe, after billions of years of slowing, began to speed up. This is why we live in such a special time, the era when dark energy has taken control, actively reshaping the future fate of everything. This accelerating expansion, driven by dark energy, points toward a profoundly lonely and cold final state for the cosmos. The most likely fate, based on everything we now observe, is known as the Big Freeze or heat death. It is the ultimate victory of emptiness over structure, a quiet and gradual fading of all that exists. As the expansion continues to accelerate, distant galaxies will not merely become fainter, they will be physically ripped away from our view. Each galaxy cluster will eventually find itself isolated, its neighbors pulled beyond a cosmic horizon as the space between them expands faster than light can traverse it. The universe will not tear apart violently, but it will dissolve into islands of matter forever separated by an ever-widening, insurmountable void. Within these isolated island universes, the raw material for creation will slowly vanish. Galaxies are vast recycling plants, where dying stars seed clouds of gas with the heavy elements needed to form new stars and planets. But as galaxies are flung apart, this cosmic cycle will grind to a halt. The existing stars will burn through their fuel, one by one, winking out into darkness. New stars will fail to ignite, as the galactic gas clouds are stretched too thin to ever collapse again. The last generations of stars will fade, leaving behind a cosmic graveyard of black holes, neutron stars, and cold, dead planets. The temperature of the entire universe will plummet, asymptotically approaching absolute zero, the point where all molecular motion ceases. This is the heat death, a state of maximum entropy where no energy can be transferred, no work can be done, and no complex structures can exist. It is a stark contrast to the universe's violent, energetic birth in the Big Bang. That beginning was all about concentration, a hot, dense fireball of pure potential. The end is all about dissipation, a cold, infinitely thin haze where every last bit of energy has been spread evenly across an unimaginable void. This final equilibrium is the universe's most profound and irreversible silence, a frozen darkness where time itself may lose all meaning. But the Big Freeze is not the only possible future. There exists a far more violent and dramatic alternative, a cosmic doomsday scenario known as the Big Rip. This fate hinges on a terrifying possibility. What if dark energy is not constant? What if its repulsive strength actually grows more powerful over time? In our current model, dark energy is a steady force, a constant pressure in every cubic centimeter of space. But some theories suggest it could be a phantom, a form of dark energy that intensifies as the universe expands. In this scenario, the acceleration would not just continue, it would run away with itself, becoming exponentially more ferocious with each passing moment. The end would not be a slow, cold fading, but a sudden, catastrophic shredding of reality itself. First, the accelerating expansion would become so powerful that it would overcome the gravitational glue holding the largest structures together. Galaxy clusters, those immense cities of thousands of galaxies, would be the first to be torn asunder. Their member galaxies would be flung apart into the ever-widening void. Next, the force would grow strong enough to rip apart individual galaxies. The Milky Way, Andromeda, and all the stars within them would be scattered like dust in a hurricane. Then, the horror would come closer to home. The expansion of space itself would become stronger than the gravity holding our solar system together. The sun would be ripped from its planets, and the planets would be torn from their orbits, cast adrift into an incomprehensible emptiness. But the destruction would not stop there. As the phantom energy continues to intensify, it would eventually surpass the very forces that hold matter together. The same expansion of space that tears galaxies apart would then attack planets and stars directly. A planet like Earth would be literally pulled apart, its mountains, its crust, and its core shredded by the stretching vacuum. Finally, in a last, unimaginable instant, the force would become stronger than the nuclear forces binding atoms together. Every molecule, every atom, every proton and neutron would be torn asunder. The very fabric of space-time would be ripped to pieces, ending the universe not with a slow freeze, but with a single, violent, and final scream. A new kind of cosmic messenger arrived on Earth on August 17, 2017. For the first time in history, astronomers detected the ripples in spacetime from colliding neutron stars, a cataclysm known as GW 170817. But this event was more than just a gravitational wave signal. It was a complete cosmic package. Along with the ripples came a brilliant flash of light across the electromagnetic spectrum, from gamma rays to visible light. This combination gave scientists a powerful new tool to measure the universe's expansion. The gravitational waves themselves carried vital information about the intrinsic strength of the collision. Just as a loud sound is from a nearby source and a faint sound is from far away, the amplitude of the gravitational waves told physicists the true distance to this colossal event, without needing a single rung of the cosmic distance ladder. Meanwhile, the accompanying flash of light, a kilonova, allowed telescopes to identify the host galaxy and measure its redshift, revealing how fast it was receding from us. For the first time, we had two independent measurements from the same event: the true distance from the gravitational waves and the velocity from the light. This was a direct, one-step measurement of the Hubble Constant, completely independent of Cepheid variables, supernova, or the cosmic microwave background. The result from this single, groundbreaking event fell intriguingly between the two conflicting values. It did not definitively side with the local or the early universe measurement, but it proved the method's immense potential. As we detect more of these cosmic collisions, this new gravitational wave siren will provide an entirely independent check on the Great Hubble tension, offering a fresh and direct path to resolving the most pressing mystery of our cosmos. Another frontier in this cosmic measurement war lies in the hearts of distant monsters, quasars. These are not stars, but the intensely bright cores of ancient galaxies, powered by supermassive black holes feeding on surrounding matter. Their staggering luminosity makes them visible from billions of light years away, but their wild variations in brightness have always made them unreliable as distance markers. They were like unpredictable lighthouses, flashing with no set pattern. Now, astronomers are trying to tame these beasts using a cosmic trick of the light called gravitational microlensing. Imagine a quasar is a brilliant, distant lamp. Between it and us, a lone star or even a planet in a foreground galaxy drifts into perfect alignment. The gravity of this intervening object acts like a lens, bending and focusing the quasar's light. For a brief period, the lamp appears to grow dramatically brighter, then fades back to normal as the lensing object moves on. This temporary brightening is not random. It follows the precise physics of gravity's lens. By carefully analyzing the pattern and duration of this brightening, scientists can calculate the physical size of the quasar's inner region. And crucially, if you know an object's true physical size, and you can measure its apparent size in the sky, you can calculate its distance directly. This turns a chaotic, flashing quasar into a measurable ruler. Each microlensing event is a delicate, one-time experiment, but collectively they offer a brand new path to measuring cosmic distances, completely independent of the supernova and Cepheid ladder. By peering into the hearts of these ancient beacons and watching for the subtle focus of gravitational lenses, we are building a new bridge across the cosmos, one that might finally show us which side of the Hubble tension holds the real truth. This cosmic tug-of-war is controlled by a budget almost entirely composed of phantoms. If you were to account for every single component of the universe, the result would be utterly humbling. The stars, planets, gas clouds, and every one of us, all the tangible stuff we consider to be reality, accounts for a mere 5% of the cosmic total. This normal matter is just the visible frosting on a cake made of unknown ingredients. The remaining 95% is dark, invisible, and dictates everything. About 27% is dark matter, the invisible scaffolding that holds galaxies together and whose gravity governed the expansion for billions of years. But the true master of the universe's fate is dark energy, making up a staggering 68% of everything. This means the force driving the accelerating expansion, the very phenomenon that is determining the ultimate destiny of all existence, is a complete and total mystery. We feel its effects, we measure its consequences, but we have no idea what it is. The fate of the cosmos is not being written by the brilliant galaxies we see in our telescopes, but by these two vast, unseen dominions, one pulling with gravity and the other pushing with a repulsive force we cannot comprehend. That principle of no center, of a universal expansion witnessed by every galaxy, rests on a deeper, more profound assumption. It is called the cosmological principle, and it is the quiet, unshakable foundation upon which all of modern cosmology is built. This principle makes two simple but staggering claims about the universe when we view it on the largest possible scales. First, it says the cosmos is homogeneous. This means the universe is essentially the same everywhere. The mix of galaxies, galaxy clusters, and vast cosmic voids is uniform throughout space. A cube of space 1 billion light-years on a side placed anywhere in the cosmos would contain roughly the same amount of stuff, arranged in the same web-like pattern, as any other cube of the same size. It is not perfectly smooth, of course. We have our local galaxies and empty spaces. But when you zoom out far enough, these variations average out into a consistent cosmic fabric. Second, the principle states the universe is isotropic. It looks the same in every direction you look. There is no preferred axis, no cosmic north or south. From our vantage point, the distant universe appears equally filled and structured, whether we peer toward the constellation Orion or in the exact opposite direction. This is why we can so confidently apply our local measurement of the Hubble constant to the entire cosmos. We are not in a special place. Our galaxy is not perched on a cosmic mountaintop with a unique view. We are in an utterly average neighborhood, and the physical laws and expansion rate we measure here are the same as those governing a galaxy 10 billion light-years away. Without this principle, cosmology would be nearly impossible. Every measurement would be suspect, a mere local curiosity with no universal meaning. The cosmological principle grants us the incredible power to extrapolate from our tiny, single data point, planet Earth, to the nature of the entire observable universe. It is the ultimate act of scientific humility, asserting that we are nowhere special. And it is that very mediocrity that allows us to understand everything. Even galaxies are not perfectly adrift on the cosmic river. Their motion is a complex dance of two distinct forces. The first is the Hubble flow, the smooth, relentless backdrop of expansion that carries all galaxies away from each other as space itself stretches. This is the pure universal recession, but superimposed on this grand drift are what astronomers call peculiar velocities. These are the individual, local motions of galaxies, caused by the gravitational tug of their neighbors. A galaxy might be pulled toward a massive cluster, or two galaxies might be orbiting each other, adding their own speed on top of the cosmic expansion. Think of it like leaves floating down a wide, slowly moving river. The river's current is the Hubble flow, carrying every leaf along. But a leaf might also be caught in a small whirlpool or be pushed by a gust of wind. Those extra local movements are its peculiar velocity. To measure the true expansion rate of the river itself, you must first subtract the leaf's own scurrying. This is precisely what astronomers must do for our own home. The Milky Way is not perfectly at rest within the Hubble flow. We are being pulled, along with our entire local group of galaxies, toward the immense gravitational monster known as the Great Attractor, a massive concentration of matter in the direction of the Centaurus constellation. Our peculiar velocity, over 600 kilometers per second, is a significant component of our total motion. When we look at a distant galaxy and measure its redshift, that number is a combination of the clean expansion of the universe and our own local gravitational sprint. To find the true Hubble constant, we must carefully subtract our own motion from the equation, filtering out the local wobble to hear the pure, deep note of the cosmos expanding. This single number, the Hubble constant, does more than measure our present. It also points directly back to our origin. The expansion rate today is a key that unlocks the age of the universe itself. In its simplest form, the age of the cosmos can be estimated by taking the inverse of the Hubble constant. Think of a car on a long, straight road. If you know its current speed, and you assume it has been traveling at that same speed the entire time, you can easily calculate how long it has been on the road by dividing the total distance traveled by its speed. The universe's journey is similar. If we take the current expansion rate and, for a moment, imagine it has been constant throughout history, running the cosmic film backward would show all galaxies converging to a single point. The time it takes to rewind to that point is the inverse of the Hubble constant, giving us a rough timeline for the entire cosmos. With our current best measurements, this simple calculation yields an age of roughly 13.8 billion years. But this is the most stunning part. This number is not isolated. It is a chorus of agreement from completely different corners of cosmology. The oldest stars we can find in the Milky Way, dated by their composition and stellar evolution models, are also just over 13 billion years old. And the cosmic microwave background, that pristine snapshot of the infant universe, tells the exact same story through the subtle patterns of its temperature fluctuations. That three completely independent lines of evidence, the expansion rate today, the aging of ancient stars, and the echo of the Big Bang, all converge on the same number, is one of the most powerful validations of our entire cosmological model. It tells us that the story we have pieced together, while still holding deep mysteries like dark energy, is fundamentally correct in its broadest strokes. We live in a universe that is 13.8 billion years old, and we know this because we can read the speed of its flight. That initial, ferocious expansion of the Big Bang was just the beginning. To understand the very fabric of our cosmos, we must rewind further to a split second so brief it defies imagination. In the first sliver of a second after everything began, the universe underwent a growth spurt of almost impossible speed, a phenomenon known as cosmic inflation. This was not the steady expansion we measure today with the Hubble Constant. This was an exponential explosion of space itself, where the universe doubled in size over and over again, faster than the speed of light, until it was astronomically larger than the moment before. This concept of inflation solves profound puzzles about the universe we see. Why is the cosmos so incredibly uniform in all directions, with the cosmic microwave background appearing almost exactly the same temperature everywhere? Without inflation, there would have been no time for these distant regions to communicate and even out their energy. But inflation took a tiny, homogeneous patch of the infant universe and stretched it to become our entire observable cosmos, explaining its smoothness. And what planted the seeds for galaxies? Inflation's incredibly rapid stretching would have magnified tiny quantum fluctuations, the microscopic jitters inherent to space itself, into the faint ripples in density that gravity would later sculpt into the vast cosmic web of galaxies and clusters. Every star, every planet, every structure we see today owes its existence to those quantum seeds, stretched to cosmic proportions during that first, fleeting moment of hyper-expansion. Another powerful tool for measuring the cosmos comes from the universe's own first cry. In the hot, dense plasma of the first few 100,000 years, the universe was a seething ocean of particles and light. Ordinary matter, which scientists call baryons, was locked in a constant struggle with radiation. Gravity would try to pull the matter together into clumps, but the intense pressure from the radiation would push it back out, creating vast, spherical sound waves that rippled through the primordial soup. These were not gentle whispers, but the loudest sonic booms in all of existence, traveling at over half the speed of light. Then, the universe cooled just enough for atoms to form, in an event known as recombination. The light, now freed, streamed away as the cosmic microwave background, and the matter, suddenly released from the pressure of radiation, was left frozen in place. The rippling sound waves stopped dead in their tracks, leaving a permanent, spherical imprint in the distribution of matter. Each of these frozen waves is a standard ruler, a single, consistent size etched into the fabric of the cosmos. That specific size, about 500 million light-years across, is the Baryon acoustic oscillation scale. Today, we can see the ghost of these ancient sound waves by mapping the positions of millions of galaxies. Galaxies have a subtle tendency to cluster at a specific distance from each other, a preferred separation that is the radius of that primordial bubble. By measuring the apparent size of these imprints in the sky at different distances, we can track how the universe has stretched over billions of years. If the imprints in an ancient, distant part of the universe appear smaller than expected, it means space has stretched less than our models predict. If they appear larger, it means expansion has been more vigorous. This gives us a direct, geometric measurement of the expansion history, a completely independent path to constraining the Hubble constant that relies on neither supernova nor the detailed physics of the cosmic microwave background. It is the fossilized echo of the universe's first sound, still ringing through the cosmos and telling us how fast it is growing. The resolution to this cosmic standoff may lie with a new generation of eyes on the sky. The James Webb Space Telescope, with its immense golden mirror and sensitive infrared instruments, is already turning its gaze toward the Cepheid variables that form the foundation of our distance ladder. From its perch a million miles from Earth, it sees through the cosmic dust that has plagued ground-based observations for a century. Its vision is so sharp, it can distinguish individual Cepheids in the crowded cores of distant galaxies, a task that was nearly impossible for the Hubble Space Telescope. This clarity is systematically eliminating one of the largest potential sources of error, refining our measurement of the first crucial rungs with breathtaking precision. But the assault on the Hubble tension does not stop there. The upcoming Nancy Grace Roman Space Telescope will take a different, equally powerful approach. Instead of staring intently at a few key targets, Roman will open a wide-angle lens on the cosmos. It is designed to perform vast, rapid surveys of the sky, discovering not just dozens, but thousands of Type Ia supernovae. This enormous statistical sample will wash away the uncertainties that come from studying a handful of these cosmic bombs. It will see so many supernovae across such a vast range of distances that it can map the expansion history of the universe with a fine-toothed comb, revealing exactly when and how the acceleration began to dominate. Furthermore, Roman will pinpoint millions of quasars and galaxies, applying the Barrian acoustic oscillation technique on an industrial scale. Together, Webb and Roman represent a pincer movement on the problem. Webb tightens the local measurement, securing our base of operations, while Roman marches out into the deep universe, charting its history with relentless, data-driven force. Their combined findings over the next decade will deliver a verdict, either confirming the tension as a true crisis and pointing unequivocally toward new physics, or finally revealing the subtle, hidden error that has eluded us for so long. The fate of our cosmological model now rests with these silent, mechanical sentinels now taking their posts in the void. This expansion is not a motion through space, but a stretching of space itself, a subtle distinction with profound consequences. The technical term for this is metric expansion. The metric is the fundamental rulebook for measuring distances within the fabric of spacetime, as described by Einstein's theory of general relativity. When we say the metric is expanding, we mean the very definition of a centimeter or a light year is changing. The cosmic grid lines are being redrawn to be farther apart. This leads to a fascinating and often overlooked question. If space is stretching everywhere, why isn't Earth getting farther from the Sun? Why isn't the Milky Way tearing itself apart? The answer lies in a cosmic tug-of-war. On one side, you have the relentless, gentle pull of dark energy, urging space to expand. On the other, you have the powerful local grip of gravity. Within a system like our solar system, the gravitational bond between the Sun and its planets is immensely strong. That force easily overpowers the minuscule effect of cosmic expansion on such a relatively tiny scale. Think of it like a powerful spring connecting two objects. The gentle, steady pull of the expanding fabric of space is far too weak to stretch that spring apart. The same is true for our entire galaxy, held together by the gravity of its stars and its vast halo of dark matter. So while the space between galaxy clusters is growing relentlessly, the space within those clusters, and within the solar systems they contain, remains stable. We are not being slowly pulled apart from within. We live in gravitationally bound islands, stable neighborhoods within an ever-widening cosmic ocean. This boundless expansion leads to one of the most mind-bending facts of all. The universe itself has no edge. There is no cosmic wall, no barrier you could ever reach, no sign declaring the end of existence. If you could build a ship and fly in one perfectly straight direction forever, you would never find a boundary. You might, in fact, eventually return to your starting point from the opposite direction. How is this possible? The key lies in the true shape of the cosmos. Our universe could be finite yet unbounded, much like the surface of a sphere. Think of the Earth. If you start walking in one direction, you never encounter an edge. You simply loop the globe and return home. The surface of the Earth is finite. You can measure its total area, but it has no boundary. The universe may be a three-dimensional version of this. We are not talking about the universe being inside a giant sphere, but the very fabric of three-dimensional space itself being curved in a higher dimension, wrapping back around on itself. In such a closed universe, a beam of light traveling for trillions of years would eventually complete a full circuit of the cosmos. This directly connects to the expansion we have been discussing. The stretching of space is not an explosion from a central point out toward some distant edge. It is happening uniformly everywhere at once, like the surface of that balloon inflating. Every location, from our galaxy to the most distant quasar, experiences itself as the center of this expansion, with all other points moving away. A universe with an edge would require a center, a special location from which the expansion began. But the cosmological principle tells us no such place exists. We are nowhere special. The expansion itself is the most powerful evidence we have for a cosmos without a center, and therefore without an edge. We are adrift on an infinite sea, or perhaps sailing a finite ocean that curves back on itself, but in either case, there is no shore to find. The very atoms that construct your body hold a secret history of the cosmos. Every element essential for life, from the calcium in your bones to the iron in your blood, was forged in the heart of ancient stars. The hydrogen in the water that flows through your veins is the only primordial exception, a relic from the Big Bang itself. All the rest, the carbon, nitrogen, and oxygen, were created in the nuclear furnaces of massive suns that lived fast and died violently. When those stars exhausted their fuel, they did not fade quietly. They erupted in spectacular supernova explosions, scattering their newly forged elements across the galaxy like cosmic seeds. This stardust eventually coalesced into new solar systems, planets, and ultimately into us. This means you are physically connected to a universe that no longer exists. The stars that built you shone brightly billions of years ago, when the cosmos was far more compact. The galaxies were closer together, space was denser, and the expansion was still in its slower, gravity-dominated era. We are not merely observers of cosmic expansion. We are its living artifacts, composed of material from a time when the universe felt much more intimate. The same expansion that now pushes galaxies apart once squeezed those stellar forges close enough to create the building blocks of life. So when you look up at the night sky, you are not looking out at a distant, separate reality. You are looking back at your own origin, a home you can never return to, carried within you with every breath you take. This accelerating expansion carves a permanent and growing horizon around every observer in the cosmos. For any future civilization that might arise billions of years from now, the universe will be a profoundly lonely place. The light from galaxies beyond our own local cluster will have been stretched by the expanding space to such long wavelengths that it becomes undetectable, and eventually, the expansion will be so fast that their light will never reach us at all. Those distant islands of stars will have vanished over the cosmic horizon, receding into a permanent, impenetrable darkness. The evidence for the Big Bang, the cosmic microwave background, will have faded into an almost imperceptible whisper, its energy diluted by an unimaginably vast and empty universe. Their night sky, though still filled with the stars of their own galaxy, will be largely black, offering no clue to the grand, bustling cosmos we see today. They will have no way of knowing that the universe is expanding, or that it began in a fiery explosion. They will live in an island universe, forever isolated, with a history that is largely unknowable. This makes our present era, right now, a uniquely privileged moment in the entire history of the cosmos. We exist at a special crossroads in time, a brief golden window where the universe has expanded enough to be transparent and safe for life, but not so much that it has erased its own history. We can still see the ancient afterglow of creation with one hand, and with the other, we can map the galaxies rushing away from us. We are the first generations to even know that the cosmos had a beginning, and we are the last who will be able to see the evidence for it so clearly. This is not just a scientific opportunity, it is a profound moment of self-discovery. By looking out and measuring the expansion, we are not just charting the fate of the universe, we are understanding our own place within it. We are temporary inhabitants of a fleeting era of cosmic clarity, gifted with the ability to read the story of everything before the final pages are torn away by the relentless, accelerating wind. From the rhythmic pulse of distant stars to the faint echo of the Big Bang, we have traced the story of a cosmos in flight. Edwin Hubble revealed a universe stretching itself thin, a discovery that gave us the Hubble Constant, the universe's own speedometer. We learned to build a ladder to the stars, using Cepheid variables and perfect supernova explosions to measure this grand expansion. Then came the greatest shock of all, the realization that this expansion is not slowing down, but accelerating, driven by a mysterious force we call dark energy. And now we stand at the precipice of a new mystery, the Hubble tension, where the universe's present speed refuses to match the story told by its ancient light, hinting that our map of reality is incomplete. This entire journey, from a static sky to an accelerating void, underscores a profound truth. We are not merely living in the universe, we are the universe awakening to itself, gifted with a fleeting moment of cosmic clarity to ask these grand questions. We are temporary witnesses to an epic whose final chapters are still being written by forces we have only begun to fathom. What do you think lies beyond our current understanding? Share your thoughts and questions in the comments below.